Welcome everybody to this parallel session on functional materials and devices. My name is Arash Mostofi, and it's my pleasure to introduce the first speaker of the session. This is an invited talk. It's Professor Kristian Thygesen from the Technical University of Denmark, who's going to be telling us about highly tunable quasi-particles in 2D materials. Over to you, Kristian.
Okay, thank you very much, Arash, and thanks to you and the other organizers for the invitation. Would have been fantastic to be in London, of course, and have a real meeting. I guess we have to wait a little bit before we can do that again. Yeah, so as Arash said, I'm going to talk about 2D materials, in particular certain types of quasi-particles and how they can be controlled by different means and what they could be used for in practice. So, so why are we interested in two-dimensional materials? There are lots of good reasons. I've listed some of them here, but it's really because these 2D materials, they host some really interesting types of quasi-particles, electrons with photons, electrons coupled with each other, electrons and holes, Cooper pairs. All these types of quasi-particles exist in these two-dimensional materials, and they can really be tuned to a level that cannot be achieved by conventional materials. And then I've added another thing down here, because what we're doing in my group is developing and applying first principles theory, and these systems also are really unique for testing and also advancing such kinds of methods. Okay, so the outline is very simple. First, talk about how the dielectric environment of a two-dimensional material can be exploited to tune quasi-particles, in particular excitons, in two-dimensional semiconductors. And then I'll move on in the second half and talk about how we can control and tune the energy of a particular type of excitons known as interlayer excitons in 2D materials, where we have a bilayer where the electron is in.
Kristian, we've lost your voice. Kristian, we've lost your voice. Oh, he can't hear us. We've lost Kristian's sound. He doesn't quite know that that's happened. Let me see if I can grab his attention.
Shall I stop his presenting?
Yeah, let's do that, because otherwise he won't know. Kristian, can you hear us? Kristian? He can't even hear us. I think he's lost all sound. Let's try to send him a message.
Mark already sent him a message. The problem is that probably he doesn't see it because it's full screen.
Okay. Maybe if I turn off his video, let's see if he notices. Kristian, can you hear us? Goodness. Didn't predict this happening. Let's see. How do we get him back?
He doesn't get the questions in full screen.
Yeah.
That's the problem. I think I will post the session, and that should throw him in backstage again. So don't run away.
Okay, let's pause the session. So we're just going to pause the session, see if we can get Kristian back. Actually, let's see whether resuming actually resets things sufficiently. Okay, everyone, it looks like we've had a technical problem and we've lost sound from Kristian Thygesen. And it seems we have no way of actually getting in touch with him. He might even be unaware that this has happened. So we're going to press ahead while we try to get hold of Kristian. We're going to press ahead with the second talk, which is given by Alex Armstrong from York. And his talk is a contributed talk entitled Bandgap Engineering in Strained Monolayer and Few Layer Molybdenum Disulfide. So over to you, Alex.
Yeah, thank you very much. So yeah, my talk is on bandgap engineering in strained monolayer and few layer molybdenum disulfide. So just a bit of background on molybdenum disulfide. It's a 2D material, Van der Waals material, so it's got quite large gaps between different layers, which are governed by the Van der Waals forces. And it has a hexagonal structure, as you can see on the right here. So it's quite a high symmetry system. It also has an interesting property where it has a direct bandgap when it's in the monolayer form, because so it has a direct bandgap in the monolayer form, and when it's in the bulk form, it only has a indirect bandgap, which means it's a 2D highly efficient light emitter, but only when it's in the monolayer form. Although you can still measure photoluminescence when it's in the bulk form, it's just a lot less intensity. So one of the interesting things about 2D materials is that they're quite tunable. So one thing that you can use to tune the bandgap of this material is you apply strain to this material. So that's quite useful for applications when you're looking to control the wavelength of light you're emitting. For example, if you wanted to use this as some sort of light source, so maybe in a laser or something, if you wanted to control the wavelength, you could apply some strain, and then you're changing the bandgap and it changes the wavelength. So it's already known quite well that the strain, applying strain in the monolayer and bulk has the effect of reducing the bandgap. The bandgap energy. So, but what's less well investigated is how this affects how strain affects the bandgap in few layer sort of systems. So that's something that I've been looking at. So just a few things on the method. So I've been modeling the system using density functional theory. This is a image of the unit cell I've been using on the right hand side here. I've been using the VASP code, which uses plane wave basis sets, which is useful for this for systems such as this because of the repeating structure. The plane wave cutoff was 520 EV, and I've used a relatively dense K-point grid of 8 by 8 by 1. This was required so we could have reasonably well converged properties. I've also used because I've been using supercells, because I've been modeling monolayer and few layer systems, the vacuum gap I've used has been a minimum of 10 angstroms. In terms of applying strain, I've just included on the right here just a diagram just to show how this sorts of strains would be applied experimentally. So you can see it's affixed to the substrate on either side with a sort of wrinkle in it, which applies the strain in this central area here. So initially, what we had to do was assess which functionals we needed to use to give reasonable properties compared to experiment. So we tested a few functionals. Firstly, we looked at PBE without any spin-orbit coupling. Then we looked at PBE with spin-orbit coupling. Then we included D3 corrections into this to include van der Waals forces. We then looked at a hybrid functional HSE06 and HSE06 including the D3 corrections. Now, all of these, apart from the first one on the left, did include spin-orbit coupling. So what we can see on this left graph here is the lattice constants for these different functionals. So you can see the only functionals that produced reasonable lattice constants compared to experiment were these ones that included the D3 corrections, so including the van der Waals forces, which makes sense because these large interlayer distances are governed by van der Waals forces because it's quite a large distance. So this shows that of the two, HSE06 plus D3 did get the lattice constants slightly closer to experiment than the PBE. If you then go look at the graph on the right, we've got the band gaps that were predicted by these various different functionals. So what this shows is that so what we wanted to compare here is this experimental line here, the black line, is the indirect band gap because this was tested on the bulk. So indirect band gap is the experimentally measured one. So these blue bars here, we can see that the HSE06 plus D3 also gets the band gap slightly better. And although the PBE is relatively close to this experimental data, the HSE06 plus D3 is slightly above, which is slightly better than being below, because what we're measuring here with DFT is the fundamental band gap, whereas experimentally you tend to measure the optical band gap, which includes the exciton binding energy. So the fundamental band gap should be slightly above what we measure experimentally. So from this, we basically came to the conclusion that HSE06 plus D3 was the way to go. Okay, so I've included here just a band structure of the bulk molybdenum disulfide. So this just to show what transitions I'm talking about. So the indirect band gap that we measure in the bulk is from the gamma point to the K point, as you can see, to the gamma K midpoint, as you can see here. And then when we move to the monolayer, the transition is just at the K point here. You can also see from this band structure, this sort of splitting at the K point here. And this shows that this only arises when you include the spin-orbit coupling, which is why we then have included spin-orbit coupling in most of the functionals that we've tested here. So in terms of how we applied the strain to the system, we tried two different methods. So this method A here was where we stretched the system along the X direction and fixed the dimensions of along the X direction of the system, and then we optimized along the B lattice vector here to keep the angle between the A and B lattice vectors constant. We then tested this by changing the angle of the optimized structures, changing the angle between the A and B lattice vectors here, by increasing it by 0.5 degrees and decreasing it by 0.5 degrees. What we found from that was that a slight increase in this angle was a slightly lower energy. So that suggests that this wasn't a very physical way of applying the strain. So what we then did was did a similar thing, but instead of optimizing along the B direction, we optimized along the Y direction here, which allowed for a change in angle here. Now we performed the same tests there and found that this was this did line an energy minimum. So this is what we then went on to use. So we then also tested applying strain along different crystal directions. So we applied it at 0, 15, 60, and 90 degrees. So the way I define those angles, you can see here, is the angle between the A lattice vector and the direction we were applying the strain in. So this is a graph for the monolayer uniaxial strain. So what we can see here is the gradient is the bandgap energy as a function of applied strain. This is along the lattice vector A, so just along the x direction. So this is the direct transition here and the indirect transition here. So you can see at a certain point they're going to cross over, and it's going to move from a direct gap to an indirect gap. The figure of merit I used for this was the gradients of these graphs, the gradients of these lines. So what we found here was that firstly the bandgap decreased roughly linearly with strain, and I then applied a fit to that and calculated a gradient. So we found for the direct gap this was 52 MeV per % of strain, and the indirect gap was 95 MeV per % strain. So because this is experimentally, because this is the monolayer and it's a direct bandgap, this was the only transition that we could find data for experimentally, but it was for the direct bandgap. But this 52 MeV per % strain fits comfortably within the range that experimentally has been reported for this. So here we have a table just summarizing the different directions of this strain and how the bandgap changed, the gradients changed there. So basically, it was very, very similar. So most of the directions, all the directions we applied were relatively consistent. So the reason we used these different directions was the 0, 60, and 90 degrees relatively high symmetry directions. So we wanted to look at those, and they found that we applied those first, and we found that these were giving relatively similar gradients. And then we wanted to apply a non high symmetry direction, this 15 degrees, just to check that this was still the case for a non high symmetry direction, and we found that it was. This is useful because it means that if you want to apply strain to your crystal, it doesn't matter. You don't have to think about the orientation of your crystal, which is quite difficult to. It's quite a difficult thing to align experimentally. We also applied biaxial strain.
Just a couple of minutes, Alex.
Okay. So we also applied biaxial strain to the monolayer. We found that very, very, very similar sort of graph, but with slightly larger gradients. So this is probably firstly, this is slightly easier to apply biaxial strain experimentally, but also you can get, because the gradient's larger, you can achieve a larger change in bandgap energy for a smaller amount of strain. So this is probably the one you would go for if you were wanting to apply this experimentally. So for the few layers biaxial strain, what this graph shows here is similar to the previous graphs I've shown, where we calculated the gradient of the indirect gap and the direct gap as we increase the strain. I've shown that gradient. So each of these data points is that gradient, but shown for different numbers of layers. So what we can see is as the number of layers increases, the indirect bandgap gradient decreases, and the whereas the direct gradient stays roughly constant. So yeah, the three main conclusions, that the bandgap decreases with uniaxial strain, but that this is independent of strain direction, so you don't need to think about the orientation of your crystal when you're applying strain. The bandgap gradient with respect to strain increases in magnitude for the biaxial case, so this is probably the one you would, the type of strain you would want to apply experimentally, because you have to stress your crystal less in each direction to get the same effect. And also that the gradient decreases with number of layers. For the indirect gap, whereas it is roughly constant for the direct gap. So yeah, just a few acknowledgements. My supervisors, Professor McKenna and Dr. Wang. Also my research group at York. The EPSRC for providing funding for the project. And also the MCC for who provided time on Archer 2 to actually run some simulations.
Alex, thank you very much for a very clear talk. We have a question from Mirta Gruning. Did you tune the HSE parameter? Is one question, and then she's asking whether the effect of dispersion on the gap is due to the geometry, the effect it has on geometry.
So no, we left the HSE parameters as standard, so we didn't change the screening parameters or anything like that. I'm not sure what you mean by the
D3.
I'm not sure what you mean by the effect of the D3.
Let's get Mirta
geometry.
Let's get Mirta on stage to ask her to clarify.
Yeah.
Mirta, do you want to clarify that question?
Yes, so the question was, so you had PBE and PBE plus D3, and there were different bandgap. So I was wondering whether this was due to the fact that the lattice constant that you found was different. So that was the question.
Yes, yeah, exactly. So it's because this including the D3 parameters is basically including the van der Waals forces. So it massively changes the interlayer distance. So yes, yeah, it's because of that. So the layers are then closer and they interact more. So yeah, it changes the electronic structure. Yeah.
Okay, thank you very much.
Thanks, Mirta. And we have one more question. Your conclusion is specific to MOS2 only, or is it more broad, do you think, to other TMD systems?
Yes, this is specific to MOS2 only. It's very much, especially this directional dependence. So I've been looking at another material recently, TIS3, and that is sort of the direction you apply the strain on massively changes. The effect is massively dependent on the direction, where it's not for this material. So yes, this is specifically for MOS2. Yeah.
Great, thank you. Okay, thank you very much, Alex, for a great talk. So we have Kristian back, and I think he has sound. I guess at least in myself. So
yes, I'm back again.
Yeah. You want to share your screen?
Yes, I am trying to do that. So I changed to Safari because I used Chrome before, and that apparently didn't work. So now it might not be working because it doesn't work with Safari.
So we can see your screen.
Share screen. But it doesn't really give me any options to choose which window I want to show. Right.
So when you share screen, it should give you options for the window.
Yeah.
You don't see?
Just go out.
Oh.
I think if you save the PowerPoint as a PDF, you can just share as a PDF.
Okay, let me try
I think
that.
that's quite good.
Sorry for this.
No, don't worry.
Okay, close that one. And try again here. And PDF. Okay, now I can choose. And let's see.
Okay, yes, yeah, we can see that. So,
Okay.
Kristian, we have 20 minutes in total. I suggest actually you use that time for a presentation, and we just sort of minimize the questions at the end. So,
Okay, so how far did I actually go before? Here, okay. All right, 20 minutes. So should I then just keep it in this mode here? You see my full screen now?
Yeah.
Okay, good. All right, so let's take a look at how the quasi-particle band structure is actually defined, and this is important in order to understand how dielectric engineering works. So if we want to measure band structure, we can use photoemission, inverse photoemission, to shoot in photons, and the electrons come out, and we measure their kinetic energy and momentum, and from that we can deduce the energy of the hole left behind. So that would be the valence states. And to calculate that, we solve the so-called quasi-particle equation that you can see here. And this is a little diagram that is actually due to Patrick Rinke that shows very nicely that when you eject an electron from a material, then you form a screening cloud around the hole. And this is something that takes place very quickly. It's a dynamical effect, but it has to be taken into account to get it. And we do that in practice using the GW approximation that I've just shown the Feynman diagram for. And with that, we can then compute these so-called quasi-particle energies. Now, let's take a look at bandgap renormalization. So here is a simple toy system that I use to illustrate the effect of dielectric bandgap renormalization. So the system is an insulator, a two-dimensional insulator, hexagonal boron nitride, that is sitting next to a layer of graphene. And when we eject an electron or insert an electron into the HBN layer, we have a screening cloud forming in the graphene layer. And that can be understood with a simple classical image charge model as shown down here. And according to that, the interaction between the electron and its image charge should depend inversely on the distance between the two. So if we compute the bandgap, we see exactly this 1 over distance dependence. If we do a GW calculation, and it converges asymptotically to the bandgap of the freestanding boron nitride layer. You can also see if we use standard DFT, then we do not have this effect, and we get the bandgap of the isolated HBN layer already when the separation is something like 4 angstroms. Okay, so now it's very impractical to have to change the dielectric environment or move the distance between different 2D materials inside a device. So we thought about other strategies for being able to exploit this effect of dielectric screening, but control it electrically. So here's a device that should be able to do exactly that. We have HBN layers here, as in this case, they are simply spacers. And then we have the graphene layer here, and we can tune the carrier concentration in the graphene layer by a gate, an electrostatic gate down here. And then we have our 2D material of interest. In this case, it's tungsten diselenide, which is a semiconductor. And by tuning the gate, we can change the concentration of carriers in the graphene sheet, and that will in turn change the dielectric environment here, because more charged carriers means better screening. And this actually works quite well. So if we try to now calculate the quasi-particle bandgap of this 2D semiconductor as a function of the Fermi level in the graphene sheet down here, then we can actually change that bandgap by more than 2 to 300 millieV. So that's a huge change in the band gap that we can induce electrically by changing the dielectric screening in the surroundings of the 2D material. So this is very different from how you do band structure engineering in conventional material, where it always involves some kind of straining, as we just heard in the previous talk, or doping or alloying of the material. In this case, we don't basically touch the material, we just change the dielectric environment. And in that way, we have a way of tuning the band gap in the material. Okay, let me just, so this is just to show that this actually is in very good agreement with a single experiment here that was performed on rhenium disulfide on graphene, on doped graphene. So it actually works and agrees with experimental data. I think actually in the interest of time, I'm going to be very quick on this part here. This is about excitons in 2D materials, where it was sort of, or has been, conventional wisdom in the field that excitons in 2D materials do not follow the standard Monolayer or hydrogen model of excitons. So the Rydberg series deviates significantly from that. And this is due to the fact that screening in 2D materials is not sort of distance independent. So this graph here shows the static dielectric function of a 2D material. That's the green curve down here as a function of in-plane wave vector, and the dashed is for the corresponding material but stacked into a bulk material. You can see for bulk, we have this assumption that we always use, that the dielectric constant is basically Q independent for small q. So this defines the static dielectric constant of the material. This doesn't work in 2D. You see a sharp increase of the dielectric function here for small q vectors. And that gives a completely different dielectric screening in the material. That is the origin of this deviation of the two-dimensional Rydberg series from the hydrogen model. And what we've shown recently is that by playing with the substrate, or by changing the substrate here, placing the 2D semiconductor on a substrate, it's actually possible to completely invert that screening such that it goes from increasing with Q to decreasing with Q, right? And that's because if you place this 2D material on a high kappa dielectric that has a dielectric constant that is larger than the intrinsic dielectric constant of the 2D material, then for small Q vectors, screening will be completely dominated by the substrate. And then you sort of invert the screening behavior, and that leads also to an inversion of the Rydberg series. So before, when the 2D material is on a weakly screening substrate, which has been in 99% of all the experiments performed so far, you see that there is the binding energy of the excitons are larger than predicted by the 2D hydrogen model. But when we go into this inverted screening regime, they're actually smaller than the hydrogen model. So in that way, we can not just quantitatively, but even qualitatively change the physics of the exciton series in the 2D material. Okay, and we also have some experimental results that demonstrate this, but I'm going to skip that in the interest of time. So now I want to move to interlayer excitons. So these are excitons where the electron and the hole are sitting in different 2D materials. And this can be achieved if we have a so-called type 2 band alignment between the two 2D semiconductors here, as sketched over here. Such interlayer excitons are really interesting because they can have much longer lifetimes than the intralayer excitons, because the electrons and the holes are really separated physically from each other. They're extremely tunable because you can apply an electric field perpendicular to the layer, and because the exciton has a out-of-plane dipole moment, you can use that electric field to tune the energy of the exciton. The downside of these excitons is that they have very low oscillator strength because the overlap of the electron and the hole is so small, and that's a problem for many applications. So let me show you a recent demonstration of an infrared photodetector that was made at the National University of Singapore This photodetector here consists of heterostructure of monolayer tungsten disulfide and hafnium disulfide here. And shining light on this will generate a photocurrent that can then be measured, and that's the way the photodetector works. What you can see here is the absorption of this device here. The blue curve shows the tungsten disulfide monolayer, and you see the peak here at 2 eV. That's due to the intralayer exciton in that monolayer. The hafnium disulfide is an indirect bandgap material and doesn't really show any features in this energy regime here. For that reason, when you form the heterostructure and you probe it, you still see the features of the intralayer excitons in the tungsten disulfide, but you also see the occurrence of 2 additional peaks at much lower energy in the infrared regime here at around 0.2 eV. And that's due to the form of an interlayer exciton here between the where the electron is sitting in the hafnium disulfide and the hole is sitting in the tungsten disulfide. And that peak can be tuned by changing a gate voltage here, a bottom gate here, because that induces, that leads to an electric field perpendicular to this interlayer excitons that can be used to tune its energy here. And by doing first principle calculations, we were able to understand the nature of these interlayer excitons. And you can look at this paper here if you want to know more details. And I should also say that the photodetector here is actually the best that has been made in that particular frequency regime here. So the mid to the long wavelength infrared regime down here. So all the red dots are from the from that study. So this was an example of a heterostructure that was used to form this required band 2, type 2 band alignment. Now it's much easier to work with homo bilayers, so MOS2 on MOS2 or tungsten S2 on tungsten S2 rather than hetero bilayers. And actually it's also possible to create these interlayer excitons in homo bilayers. And in fact, one can create excitons that are even more useful. And these are types of excitons that we call mixed interlayer excitons, where there is an intralayer exciton in one of the layers that hybridizes with a pure interlayer exciton and forms this mixed interlayer exciton. And here is a little cartoon that shows the idea. So the charge transfer exciton, or the pure interlayer excitons here, they can be tuned by an electric field here, moving up and down if you apply an electric field, or by the distance between the 2 layers. Whereas the intralayer excitons, they are not affected by an electric field or by the distance between the 2 layers. So it's possible to bring this system into a situation where the interlayer exciton hybridizes with the intralayer exciton and form this mixed interlayer exciton. And we've done calculations for homo bilayer of MOS2, and we can see that there are certain spectral features in the absorption coefficient that correspond exactly to such mixed interlayer excitons here. And the nice thing with them is that they basically combine the best of the 2 worlds because they have intralayer partly, they can have higher strengths, but at the same time, because they also have an interlayer component, they can be tuned by a perpendicular electric field. And these are experiments performed at Exeter University by in the group of Saverio Russo, where they made this kind of detector and were able to really see how such interlayer or mixed interlayer excitons form here in between the A and the B intralayer excitons. You see this cross here, where one can tune the exciton energy using the perpendicular electric field. And this can again be understood by first principle calculations. We can understand sort of which intralayer excitons can couple to which interlayer excitons and form these mixed interlayer excitons, and then we can sort of reproduce the experimental absorption coefficients here. Okay, right. I think if I have a couple of minutes left, I just want to mention a very large project that we're working on in my group here that we call the Computational 2D Materials Database, to C2DB, which is an online database of 2D materials that currently holds about 4,000 monolayers, for which we have used sort of an automated workflow to compute a range of different properties here, as listed over here to the right. And let me just highlight some of the newest properties that we have computed in this way. Topological invariance, exchange couplings in magnetic 2D materials, Born charges and piezoelectric tensors, Raman spectra for about 800 of those, and second harmonics generation spectra for about 400 materials, or all of those that do not have inversion center and have a band gap. So this, if you're interested, you can take a look in this paper here and this paper down here, where we describe the creation of this database and how you can get the database and what kind of properties you can find in there. So with that, I think I'm at the conclusions here. So I hope I convinced you that 2D materials are really interesting. They can host new types of quasi-particles. I talked mainly about excitons, but there's a zoo of other types of quasi-particles that exist in these materials. I talked a little bit about the exciton Rydberg series in 2D semiconductors and how one can tune it and change it using screening from substrates. And then I talked about mixed interlayer excitons that I think are a really interesting platform for exciton physics in general, but also for realizing excitonic devices that could operate at room temperature. And then finally, I just briefly mentioned this database project that we are working on continuously. Yeah, I think with that, I should acknowledge my collaborators and the funding agencies that have provided the money for the research. Okay, and I hope I'm not too much over time.
No, not at all.
Okay, good.
You did a great job accelerating through that one. We even have about 2 or 3 minutes for a Q&A.
Oh, good.
Which is great. So if anyone has a question, then please do put it in the chat or in the Q&A tab. I might start with one. So in the first calculation you showed with the graphene layer beneath the TMD, and you were looking at properties as a function of shopping towards the beginning. Here we go. Yeah, so was this an explicit calculation
No.
with the gate and applying a field, or
No. So in general, if you want to look at heterostructures with 2D materials, you have the nice thing with 2D materials is you can just put them together. You don't need to have lattice lattice matching at the interface, because it's just van der Waals bond. So you can put basically any 2D material on any other 2D material, and they would form a perfect atomically well-defined interface. If you want to model this, the problem is that the lattice constants of the two materials will be different, and you would need a huge supercell to account for this. So that's not really feasible in general. So what we have developed is something we call the quantum electrostatic heterostructure model, QEH model, where we can account for the dielectric environment into the calculation of the band structure of a particular 2D material. So for this stack here, we can compute the dielectric function using the QEH model. Then we can perform a GW calculation for the tungsten diselenide, where we change the W, the screened electron-electron interaction, such that it accounts for the effect of the dielectric environment. So it's actually just when we show something like these band gaps here, that's a GW calculation for the single layer here, but taking the entire dielectric environment into account through the screened electron-electron interaction. And the effect of the gate is basically to change the Fermi level position in the graphene layer. So that's how we simulate the gate. We don't have the gate explicit in the calculation.
Yeah, so that enters the dielectric function in the GW. I get it.
Yeah.
Okay, good. Thank you. Any other question? I think that's it. So let me just ask one more. Kristian, you mentioned these explicit heterostructures are very difficult and challenging unless you sort of strain one layer to lattice match. What would you say is another big challenge in simulating this computation? I mean, we know screening and getting screening right is difficult. The structural model is quite difficult. I mean, where do you think the big challenges in this area lie?
I think one of the big challenges now with these twisted heterostructures, where you can get into regimes where you have these flat bands, where you get highly correlated physics. That's obviously a very quickly moving frontier in the field where there are lots of challenges. These structures are completely beyond what you can reach with full ab initio, because something like the twisted graphene a bilayer at the magic angle has about 12,000 atoms in a unit cell. So these Moret structures, you need to address them in a different way, not by brute force ab initio. So this is one challenge, trying to combine ab initio calculations to get the parameters that you can use to set up your model Hamiltonian to study these interesting and strongly correlated materials. Right. Also getting just, the different stacking configurations, right? This is all dominated by van der Waals interactions, and different stacking configurations can have energies that differ on a few millieV energy scale. So getting that correct and predict the most stable stacking configurations in general, not just for the twisted, but also for the sort of lattice aligned heterostructures and homostructures is also quite a challenge if we talk about sort of structural properties.
Yeah, thanks. Yeah, it's good to hear your thoughts on that. Yeah.
Sure.